Good morning, good evening, and good afternoon, everyone. Welcome to this tutorial on Apache Spark, one of the most in-demand technologies and processing frameworks in the big data world. And here we will learn on Apache Spark, history of Spark, what is Spark, Hadoop, which is a framework again, Wes Spark, components of Apache Spark, that is Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and Graphx. Then we will learn on Spark architecture, applications of Spark, Spark use cases. So let's begin with understanding about history of Apache Spark. It all started in 2009 as a project at UC Berkeley AMP Labs by Mate Zaharia. In 2010, it was open sourced under a BSD license. In 2013, Spark became an Apache top-level project, and in 2014, used by Databricks to sort large-scale data sets, and it set a new world record. So that's how Apache Spark started. And today it is one of the most in-demand processing framework, or I would say in-memory computing framework, which is used across the big data industry. So what is Apache Spark? Let's learn about this. Apache Spark is an open source in-memory computing framework, or you could say data processing engine, which is used to process data in batch and also in real time across various cluster computers. And it has a very simple programming language behind the scenes, that is Scala, which is used. Although if users would want to work on Spark, they can work with Python, they can work with Scala, they can work with Java, and so on, even R for that matter. So it supports all these programming languages, and that's one of the reasons that it is called polyglot, wherein you have good set of libraries and support from all the programming languages, and developers and data scientists incorporate Spark into their applications or build Spark-based applications to process, analyze, query, and transform data at a very large scale. So these are key features of Apache Spark. Now, if you compare Hadoop with Spark, we know that Hadoop is a framework, and it basically has MapReduce, which comes with Hadoop for processing data. However, processing data using MapReduce in Hadoop is quite slow because it is a batch-oriented operation and it is time-consuming. If you talk about Spark, Spark can process the same data 100 times faster than MapReduce, as it is a in-memory computing framework. Well, there can always be conflicting ideas saying, what if my Spark application is not really efficiently coded and my MapReduce application has been very efficiently coded? Well, then it's a different case. However, normally, if you talk about code which is efficiently written for MapReduce or for Spark-based processing, Spark will win the battle by doing almost 100 times faster than MapReduce. So as I mentioned, Hadoop performs batch processing, and that is one of the paradigms of MapReduce programming model, which involves mapping and reducing, and that's quite rigid. So it performs batch processing. The intermittent data is written to SDFS and read back from SDFS, and that makes Hadoop's MapReduce processing slower. In case of Spark, it can perform both batch and real-time processing. However, a lot of use cases are based on real-time processing. Take an example of Macy's, take an example of retail giant such as Walmart, and there are many use cases who would prefer to do real-time processing, or I would say near real-time processing. So when we say real-time or near real-time, it is about processing the data as it comes in, or you're talking about streaming kind of data. Now, Hadoop or Hadoop's MapReduce obviously was started to be written in Java. Now you could also write it in Scala or in Python. However, if you talk about MapReduce, it will have more lines of code since it is written in Java, and it will take more times to execute. You have to manage the dependencies, you have to do the right declarations, you have to create your mapper and reducer and driver classes. However, if you compare Spark, it has few lines of code as it is implemented in Scala, and Scala is a statically typed, dynamically inferred language. It's very, very concise. And the benefit is it has features from both functional programming and object-oriented language. And in case of Scala, whatever code is written, that is converted into byte codes, and then it runs in the JVM. Now, Hadoop supports Kerberos authentication. There are different kind of authentication mechanisms. Kerberos is one of the well-known ones, and it can really get difficult to manage. Now, Spark supports authentication via a shared secret. It can also run on Yarn, leveraging the capability of Kerberos. So what are Spark features which really makes it unique or in-demand processing framework? When we talk about Spark features, one of the key features is fast processing. So Spark contains resilient distributed datasets. So RDDs are the building blocks for Spark, and we'll learn more about RDDs later. So Spark contains RDDs, which saves huge time taken in reading and writing operations. So it can be 100 times, or you can say 10 to 100 times faster than Hadoop. When we say in-memory computing, here I would like to make a note that there is a difference between caching and in-memory computing. Think about it. Caching is mainly to support read-ahead mechanism where you have your data preloaded so that it can benefit further queries. However, when we say in-memory computing, we are talking about lazy evaluation. We are talking about data being loaded into memory only and only when a specific kind of action is invoked. So data is stored in RAM. So here we can say RAM is not only used for processing, but it can also be used for storage. And we can again decide whether we would want that RAM to be used for persistence or just for computing. So it can access the data quickly and accelerate the speed of analytics. Now, Spark is quite flexible. It supports multiple languages, as I already mentioned, and it allows the developers to write applications in Java, Scala, R, or Python. It's quite fault tolerance. So Spark contains these RDDs, or you could say execution logic, or you could say temporary data sets, which initially do not have any data loaded, and the data will be loaded into RDDs only when execution is happening. So these can be fault tolerant, as these RDDs are distributed across multiple nodes. So failure of one worker node in the cluster will really not affect the RDDs because that portion can be recomputed. So it ensures loss of data. It ensures that there is no data loss, and it is absolutely fault tolerant. It is for better analytics. So Spark has rich set of SQL queries, machine learning algorithms, complex analytics, all of this supported by various Spark components, which we will learn in coming slides. With all these functionalities, analytics can be performed better in terms of Spark. So these are some of the key features of Spark. However, there are many more features which are related to different components of Spark, and we will learn about them. So what are these components of Spark which I'm talking about? Spark Core. So this is the core component, which basically has RDDs, which has a core engine which takes care of your processing. Now you also have Spark SQL. So people who would be interested in working on structured data or data which can be structurized would want to prefer using Spark SQL. And Spark SQL internally has components or features like data frames and data sets, which can be used to process your structured data in a much faster way. You have Spark streaming. Now that's again an important component of Spark, which allows you to create your Spark streaming applications, which not only works on data which is being streamed in or data which is constantly getting generated, but you would also, or you could also transform the data. You could analyze or process the data as it comes in smaller chunks. You have Spark's MLlib. Now this is basically a set of libraries which allows developers or data scientists to build their machine learning algorithms so that they can do predictive analytics or prescriptive, descriptive, preemptive analytics, or they could build their recommendation systems or bigger, smarter machine learning algorithms using these libraries. And then you have Graphx. So think about organizations like LinkedIn or say Twitter, where you have data which naturally has a network kind of flow. So data which could be represented in the form of graphs. Now here when I talk about graphs, I'm not talking about pie charts or bar charts, but I'm talking about network related data. That is data which can be networked together, which can have some kind of relationship. Think about Facebook, think about LinkedIn, where you have one person connected to other person or one company connected to other company. So if we have our data which can be represented in the form of network graphs, then Spark has a component called Graphx, which allows you to do graph-based processing. So these are some of the components of Apache Spark: Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and Graphx. So to learn more about components of Spark, let's learn here about Spark Core. Now this is the base engine, and this is used for large-scale parallel and distributed data processing. So when you work with Spark, at least and the minimum you would work with is Spark Core, which has RDDs as the building blocks of your Spark. So it is responsible for your memory management, your fault recovery, scheduling, distributing, and monitoring jobs on a cluster, and interacting with storage systems. So here I would like to make a key point that Spark by itself does not have its own storage. It relies on storage. Now that storage could be your SDFS, that is Hadoop's distributed file system. It could be a database like NoSQL database such as HBase, or it could be any other database, say RDBMS, from where you could connect your Spark and then fetch the data, extract the data, process it, analyze it. So let's learn a little bit about your RDDs, resilient distributed datasets. Now Spark Core, which is the base engine or the core engine, is embedded with the building blocks of Spark, which is nothing but your resilient distributed dataset. So as the name says, it is resilient. So it is existing for a shorter period of time, distributed. So it is distributed across nodes. And it is a data set where the data will be loaded or where the data will be existing for processing. So it is immutable, fault tolerant, distributed collection of objects. So that's what your RDD is. And there are mainly two operations which can be performed on an RDD. Now to take an example of this, say I want to process a particular file. Now here I could write a simple code in Scala, and that would basically mean something like this. So if I say val, which is to declare a variable, I would say val x, and then I could use what we call as Spark context, which is basically the most important entry point of your application. So then I could use a method of Spark context, for example, that is text file, and then I could point it to a particular file. So this is just a method of your Spark context, and Spark context is the entry point of your application. Now here I could just give a path in this method. So what does this step do? It does not do any evaluation. So when I say val x, I'm creating an immutable variable, and to that variable I'm assigning a file. Now what this step does is it actually creates a RDD, resilient distributed dataset. So we can imagine this as a simple execution logic, a empty dataset which is created in memory of your node. So if I would say I have multiple nodes in which my data is split and stored, imagining that your Spark is working with Hadoop. So I have Hadoop, which is using say 2 nodes, and this is my distributed file system, SDFS, which basically means my file is written to HDFS, and it also means that the file related blocks are stored in the underlying disk of these machines. So when I say val x equals sc.text file, that is using a method of Spark context. Now there are various other methods like whole text files, parallelize, and so on. This step will create an RDD. So you can imagine this as a logical data set which is created in memory across these nodes, because these nodes have the data. However, no data is loaded here. So this is the first RDD, and I can say first step in what we call as a DAG. A DAG which will have series of steps which will get executed at later stage. Now later I could do further processing on this. I could say val y, And then I could do something on X. So I could say X dot map, and I would want to apply a function to every record or every element in this file. And I could give a logic here, x.map. Now this second step is again creating an RDD, a resilient distributed data set. You can say second step in my DAG. Okay, and here you have a external RDD, one more RDD created, which depends on the first RDD. So my first RDD becomes the base RDD or parent RDD, and the resultant RDD becomes the child RDD. Then we can go further and we could say val z, and I would say, okay, now I would want to do some filter on Y. So this filter which I am doing here, and then I could give a logic. Might be I'm searching for a word, I'm searching for some pattern. So I could say val z equals y dot filter, which again creates one more RDD, a resilient distributed data set in memory. And you can say this is nothing but one more step in the DAG. So this is my DAG, which is a series of steps which will be executed. Now here, when does the execution happen? When will the data get loaded into these RDDs? So all of this, that is using a method, using a transformation like map, using a transformation like filter or flat map or anything else, these are your transformations. So the operations such as map, filter, join, union, and many others will only create RDDs, which basically means it is only creating execution logic. No data is evaluated, no operation is happening right now. Only and only when you invoke an action, that is, might be you want to print some result, might be you want to take some elements and see that, might be you want to do a count. So those are actions which will actually trigger the execution of this DAG right from the beginning. So if I here say z dot count, where I would want to just count the number of words which I'm filtering, this is an action which is invoked, and this will trigger the execution of DAG right from the beginning. So this is what happens in a Spark. Now, if I do a z.count again, it will start the whole execution of DAG again right from the beginning. So my z.count, second time an action is invoked, again the data will be loaded in the first RDD, then you will have map, then you will have filter, and finally you will have result. So this is the core concept of your RDDs, and this is how RDD works. So mainly in Spark, there are two kinds of operations. One is your transformations and one is your actions. Transformations or using a method of Spark context will always and always create an RDD, or you could say a step in the DAG. Actions are something which will invoke the execution, from the first RDD till the last RDD where you can get your result. So this is how your RDDs work. Now, when we talk about components of Spark, let's learn a little bit about Spark SQL. So Spark SQL is a component, a processing framework, which is used for structured and semi-structured data processing. So usually people might have their structured data stored in RDBMS or in files where data is structured with particular delimiters and has a pattern. And if one wants to process this structured data, if one wants to use Spark to do in-memory processing and work on this structured data, they would prefer to use Spark SQL. So you can work on different data formats, say CSV, JSON. You can even work on smarter formats like Avro, Parquet, even your binary files or sequence files. You could have your data coming in from an RDBMS, which can then be extracted using a JDBC connection. So at the bottom level, when you talk about Spark SQL, it has a data source API, which basically allows you to get the data in whichever format it is. Now, Spark SQL has something called as data frame API. So what are data frames? Data frames, in short, you can visualize or imagine as rows and columns, or if your data can be represented in the form of rows and columns with some column headings. So data frame API allows you to create data frames. So like my previous example, when you work on a file, when you want to process it, you would convert that into an RDD using a method of Spark context or by doing some transformations. So in the similar way, when you use data frames or when you want to use Spark SQL, you would use Spark's context, which is SQL context or Hive context or Spark, which allows you to work with data frames. So like in my earlier example, we were saying val x equals sc.text file. Now in case of data frames, instead of sc, you would be using, say, Spark dot something. So Spark context is available for your data frames API to be used. In older versions like Spark 1.6 and so on, we were using Hive context or SQL context. So if you were working with Spark 1.6, you would be saying val x equals SQL context dot. Here we would be using Spark dot. So data frame API basically allows you to create data frames out of your structured data, which also lets Spark know that data is already in a particular structure. It follows a format, and based on that, your Spark's backend DAG scheduler, right? So when I say about DAG, I talk about your sequence of steps. So Spark is already aware of what are the different steps involved in your application. So your data frame API basically allows you to create data frames out of your data. And data frames, when I say, I'm talking about rows and columns with some headings. And then you have your data frame DSL language, or you can use Spark SQL or Hive query language. Any of these options can be used to work with your data frames. So to learn more about data frames, follow in the next sessions. When you talk about Spark streaming, now this is very interesting for organizations who would want to work on streaming data. Imagine a store like Macy's, where they would want to have machine learning algorithms. Now, what would these machine learning algorithms do? Suppose you have a lot of customers walking in the store and they are searching for particular product or particular item. So there could be cameras placed in the store, and this is being already done. There are cameras placed in the store which will keep monitoring in which corner of the store there are more customers. Now, once camera captures this information can be streamed in to be processed by algorithms, and those algorithms will see which product or which series of product customers might be interested in. And if this algorithm in real time can process based on the number of customers, based on the available product in the store, it can come up with a attractive alternative price, so that which the price can be displayed on the screen and probably customers would buy the product. Now this is a real-time processing where the data comes in, algorithms work on it, do some computation and give out some result, and which can then result in customers buying a particular product. So the whole essence of this machine learning and real-time processing will really hold good if and when customers are in the store. Or this could relate to even an online shopping portal where there might be machine learning algorithms which might be doing real-time processing based on the clicks which customer is doing. Based on the clicks, based on customer history, based on customer behavior, algorithms can come up with recommendation of products or better altered price so that the sale happens. Now, in this case, we would be seeing the essence of real-time processing only in a fixed or in a particular duration of time. And this also means that you should have something which can process the data as it comes in. So Spark Streaming is a lightweight API that allows developers to perform batch processing and also real-time streaming and processing of data. So it provides secure, reliable, fast processing of live data streams. So what happens here in Spark Streaming in brief? So you have an input data stream. Now that data stream could be a file which is constantly getting appended. It could be some kind of metrics. It could be some kind of events based on the clicks which customers are doing or based on the products which they are choosing in a store. This input data stream is then pushed in through a Spark Streaming application. Now Spark Streaming application will break this content into smaller streams, what we call as discretized streams or batches of smaller data on which processing can happen in frames. So you could say process my file every 5 seconds for the latest data which has come in. Now there are also some Windows based options. Like when I say Windows, I mean a window of past 3 events. Window of past 3 events, each event being of 5 seconds. So your batches of smaller data is processed by Spark engine, and this processed data can then be stored or can be used for further processing. So that's what Spark streaming does. When you talk about MLlib, it's a low-level machine learning library that is simple to use, scalable, and compatible with various programming languages. Now, Hadoop also has some libraries, like you have Apache Mahout, which can be used for machine learning algorithms. However, in terms of Spark, we are talking about machine learning algorithms which can be built using MLlib's libraries, and then Spark can be used for processing. So MLlib eases the deployment and development of scalable machine learning algorithms. I mean, think about your clustering techniques. So think about your classification, where you would want to classify the data, where you would want to do supervised or unsupervised learning. Think about collaborative filtering and many other data science related techniques, or techniques which are required to build your recommendation engines or machine learning algorithms can be built using Spark's MLlib. Graphx is Spark's own graph computation engine. So this is mainly if you are interested in doing a graph-based processing. Think about Facebook, think about LinkedIn, where you can have your data which can be stored, and that data has some kind of network connections, or you could say it is well networked. I could say X is connected to Y is connected to Z is connected to A. So X, Y, Z, A, all of these are, in terms of graph terminologies, we call as vertices or vertex, which are basically being connected. And the connection between these are called edges. So I could say A is friend to B. So A and B are vertices, and friend, a relation between them, is the edge. Now, if I have my data which can be represented in the form of graphs, if I would want to do a processing in such way, this could be not only for social media, it could be for your network devices, it could be a cloud platform, it could be about different applications which are connected in a particular environment. So if you have data which can be represented in the form of graph, then Graphx can be used to do ETL, that is extraction, transformation, load, to do your data analysis, and also do interactive graph computation. So Graphx is quite powerful. Now, when you talk about Spark, your Spark can work with your different clustering technologies. So it can work with Apache Mesos. That's how Spark came in, where it was initially to prove the credibility of Apache Mesos. Spark can work with Yarn, which is usually you will see in different working environments. Spark can also work as standalone. That means without Hadoop, Spark can have its own setup with master and worker processes. So usually, or you can say technically, Spark uses a master-slave architecture. Now that consists of a driver program that can run on a master node. It can also run on a client node. It depends on how you have configured or what your application is. And then you have multiple executors which can run on worker nodes. So your master node has a driver program, and this driver program internally has the Spark context. So your Spark, every Spark application will have a driver program, and that driver program has a inbuilt or internally used Spark context, which is basically your entry point of application for any Spark functionality. So your driver or your driver program interacts with your cluster manager. Now, when I say interacts with cluster manager, so you have your Spark context, which is the entry point that takes your application request to the cluster manager. Now, as I said, your cluster manager could be, say, Apache Mesos, it could be Yarn, it could be Spark standalone master itself. So your cluster manager in terms of Yarn is your resource manager. So your Spark application internally runs as series or set of tasks and processes. Your driver program, wherever that is run, will have a Spark context, and Spark context will take care of your application execution. How does that do it? Spark context will talk to cluster manager. So your cluster manager could be Yarn. And in terms of when I say cluster manager for Yarn would be resource manager. So at high level, we can say a job is split into multiple tasks, and those tasks will be distributed over the slave nodes or worker nodes. So whenever you do some kind of transformation or you use a method of Spark context, an RDD is created, and this RDD is distributed across multiple nodes. As I explained earlier, worker nodes are the slaves that run different tasks. So this is how a Spark architecture looks like. Now we can learn more about Spark architecture and its interaction with Yarn. So usually what happens when your Spark context interacts with the cluster manager. So in terms of Yarn, I could say resource manager. Now we already know about Yarn. So you would have, say, node managers running on multiple machines, and each machine has some RAM and CPU cores allocated for your node manager. On the same machine, you have the data nodes running, which obviously are there to have the Hadoop related data. So whenever an application wants to process the data, your application via Spark context contacts the cluster managers, that is resource manager. Now what does resource manager do? Resource manager makes a request. So resource manager makes requests to the node manager of the machines wherever the relevant data resides, asking for containers. So your resource manager is negotiating or asking for containers from node manager saying, hey, can I have a container of 1 GB RAM and 1 CPU core? Can I have a container of 1 GB RAM and 1 CPU core? And your node manager, based on the kind of processing it is doing, will approve or deny it. So node manager would say, fine, I can give you the container. And once this container is allocated or approved by node manager, resource manager will basically start an extra piece of code called app master. So app master is responsible for execution of your applications, whether those are Spark applications or MapReduce. So your application master, which is a piece of code, will run in one of the containers. That is, it will use the RAM and CPU core, and then it will use the other containers which were allocated by node manager to run the tasks. So it is within this container which can take care of execution. So what is a container? A combination of RAM and CPU core. So it is within this container, we will have a executor process which would run, and this executor process is taking care of your application related tasks. So that's how overall Spark works in integration with Yarn. Now let's look at some applications of Spark. So JP Morgan Chase and company uses Spark to detect fraudulent transactions, analyze the business spends of an individual to suggest offers, and identify patterns to decide how much to invest and where to invest. So this is one of the examples of banking. A lot of banking environments are using Spark due to its real-time processing capabilities and in-memory faster processing, where they could be working on fraud detection or credit analysis or pattern identification and many other use cases. Alibaba Group, that uses also Spark to analyze large data sets of data such as real-time transaction details. Now that might be based online or in the stores, looking at the browsing history in the form of Spark jobs, and then provides recommendations to its users. So Alibaba Group is using Spark in its e-commerce domain. You have IQVIA. Now, this is a leading healthcare company that uses Spark to analyze patients' data, identify possible health issues, and diagnose it based on their medical history. So there is a lot of work happening in healthcare industry where real-time processing is finding a lot of importance, and real-time and faster processing is what is required. So healthcare industry and IQVIA is also using Spark. You have Netflix, which is known, and you have Riot Games. So entertainment and gaming companies like Netflix and Riot Games use Apache Spark to showcase relevant advertisements to their users based on the videos that they have watched, shared, or liked. So these are few domains which find use cases of Spark, that is banking, e-commerce, healthcare, entertainment, and then there are many more which are using Spark in their day-to-day activities for real-time, in-memory, faster processing. Now, let's discuss about Spark's use case, and let's talk about Conviva, which is world's leading video streaming companies. So video streaming is a challenge. Now, if you talk about YouTube, which has data, you could always read about it. So YouTube has data which is worth watching 10 years. So there is huge amount of data where people are uploading their videos or companies are doing advertisements, and this videos are streamed in or can be watched by users. So video streaming is a challenge, and especially with increasing demand for high quality streaming experiences. Conviva collects data about video streaming quality to give their customers visibility into the end user experience they are delivering. Now, how do they do it? Apache Spark again. Using Apache Spark, Conviva delivers a better quality of service to its customers by removing the screen buffering and learning in detail about network conditions in real time. This information is then stored in the video player to manage live video traffic coming in from 4 billion video feeds every month to ensure maximum retention. Now, using Apache Spark, Conviva has created an auto diagnostics alert. It automatically detects anomalies along the video streaming pipeline and diagnoses the root cause of the issue. Now, this really makes it one of the leading video streaming companies based on auto diagnostic alerts. It reduces waiting time before the video starts. It avoids buffering and recovers the video from a technical error. And the whole goal is to maximize the viewer engagement. So this is Spark's use case, where Conviva is using Spark in different ways to stay ahead in video streaming related deliveries. Thank you and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.